y1, y2 given to you. Okay, so let's say I start from a beam like this, okay. So maybe the neutral axis is here. The neutral axis is here, and y1 is measured from the neutral axis to the top. Okay, y2 is measured from the neutral axis to the bottom. Okay, right. So area will be given, moment of inertia will be given, y1, y2 will be given. Okay, with this you need to calculate S1 and S2. S1 is just equal to moment of inertia divided by y1. Okay, and S2 is moment of inertia divided by y2. Okay. Okay. In the test one, I give you the rectangular sections, right? In the test one, I give you the rectangular sections. The moment of the neutral axis is in the middle, right? Area, you need to go and calculate yourself. This is 300. This is 600, right? So area is just 300 multiplied by 600, correct? Okay. Now the reason I bring this one, because I want you to use the test one. You need to rework the test one, and also as a practice to prepare for the I. Okay. And the moment of inertia I is just 1/12 of BH cubed. This is B, and this is H. Okay, now set up. That means 1/12 of B. B in this case is 300. H is the height. B is the width. H is the height. So 1/12 of BH cubed. So 1/12 of BH cubed basically is 1/12 of 300 multiplied by 600 cubed. Okay, and the unit is millimeter fourth, right? And then y1 in this case, measured from neutral axis to the top, is 300, right? Okay. Y2 will be also 300, right? Then from there you can calculate S1 is equal to I divided by Y1, and S2 is equal to Y divided by Y2. Okay, alright. So in your test one, you base on this to calculate S1, S2, because we need the S1 and S2 to calculate the stresses. Okay, to calculate the stresses. So this part is clear. Alright. Okay. So these are the section properties. The second thing is calculation of stresses, concrete stresses, right? Calculation of concrete stresses at top and bottom, and at top and bottom, at mid-span and support. Okay, before we talk about this, let's talk about the moment. Okay, let's talk about calculation of moment first. Let me say. Here, the calculation of moment. Okay, first is the self-weight moment, right? Okay, first is so normally you have to calculate your self-weight. Okay, talk about beam self-weight. Beam self-weight is starting from 24 kilonewton multiplied by the area. Okay? Multiplied by area. This will give you kilonewton per meter. Right? This will give you, so in this case, this will be 24 kilonewton per meter cube multiplied by 0.3 meter and 0.6 meter. If I use this as an example, right? Okay, the area is 300 by 600, but because this is kilonewton per meter cube, so I need to convert the 300 millimeter to 0.3 meter and 0.6 meter. Okay, so the units is meter cancel out, becomes kilonewton per meter length. Understand? Yeah. So this is the beam cell weight. Okay, beam cell weight. Let's say I use a symbol called W0 or W cell. Okay, let's say W cell. W cell. W cell weight, right? Okay, and also the loading. This is the loading. So we have the superimposed net load. Superimposed net load. And also the superimposed live load. Okay, this is the loading. Loading on beam. Okay, so let's say this is the beam. So we have uniform load. This is the W cell weight. Okay. Then we have the superimposed net load, and then superimposed live load. Okay. So in this paper, okay. In this question, right? I don't know whether you have your paper with you. I say the beam carries live load of 15 kilonewton per meter, right? If you look at the second paragraph, see that? No?
Yes.
The beam carries live load WL of 15 kilonewton per meter. That means this is equal to 15 kilonewton per meter. This, because I didn't give you the dead load, that means 0. Okay. In the final paper, in the final exam paper, I may give you this and give you this. But in this case, I didn't give you this, I mean 0, right? And then the cell weight is from here. 24 multiplied by 0.3 and 0.6, what is that value? 4.32, right? So here is 4.32 kilonewton per meter. Okay? So when we say calculation of moment, you should draw up the beam length. I think in this case is, I think I give you 12 meters, right? 12 meters. Okay? So calculation of moment, it means you look at this diagram, the beam spanning this carry all this loading, right? So how do you calculate the simple span moment is WL squared over 8. Okay? Yeah. Alright. So the service load moment, no factor, is equal to WL squared over 8. Okay? So we have to memorize this one. WL squared over 8. Okay? Alright. And so MS service load moment is equal to WL squared over 8. And W is, this is equal to W, total, right? Okay, that means we have the W cell weight, W superimposed live load, W superimposed live load. You add all these three together, give you the total W. Understand? Okay? And then you use this one, put into here, WL squared over 8. L is this one. Okay, Understand? Okay. One thing I need to emphasize. Alright. I think okay. Alright. Okay. So now so this is the calculation of moment. Okay. So the section properties. So you started with the section properties. You just calculate S1, S2 because in the final exam paper, these values will be given to you. Okay. Alright. And then calculation of moment. Okay. Normally this will be given to you, but this one you need to calculate yourself. That's why if you look at my paper, I say the beam carry live load of 15.0 kN per meter in addition to its own weight. That means you have to include. That means this 50 kN doesn't include its own weight. That means you have to do it, calculate the own self weight yourself. Okay. Alright. So these two, make sure that you got it right. Then, okay, let me draw the moment diagram. Moment diagram of SR. Moment diagram is like this. This is the support. This is the middle. This is the middle. This is your M maximum. Okay. The maximum is equal to MS is equal to WL squared over 8. Okay. So this is the midspan. Okay. The midspan has the maximum moment. At the support here is 0 moment. Okay? At the support here is 0. This is for simply supported beam. Right? When you have a simply supported beam, the maximum moment is in the middle. Here and here, 0 moment. Okay? Alright. Why I highlight to you the midspan and the support? Because we need to do the calculation of concrete stresses at midspan and the support. Midspan and the support. Okay? Right? So, okay, let me draw this beam bigger size. That means I need to calculate the stresses, the concrete stresses at midspan and the support. The midspan and the support. Okay? At midspan, the moment is this. At support, the moment is this. Okay? Alright. So at midspan, here this is my, let's say this is the midspan. I need to calculate at the top and at the bottom. Okay? That means at the top is F1, bottom F2. Okay? And also at the support, I also need to calculate the stresses at the top and at the bottom. So this is what I mean by calculation of concrete stresses at top and bottom. At top and bottom, at midspan and at the support. Understand? Okay. So at midspan, the maximum moment is WL squared over 8. Okay? At the support, the moment is 0. Okay? At the support, the moment is 0. Is equal to 0 at support. Okay, this is at midspan. Okay? So you use the test 2 as an exercise, go through that, go through this. Now we come and do the calculation of concrete stresses. Okay. Now, part A, if you look at this part A, calculate extreme fiber stresses. Extreme fiber stresses, that means is this one, F1, F2. Extreme fiber, the top extreme and the bottom extreme. Okay. So if you look at the first question, is compute the extreme fiber at midspan and support at transfer condition. Yeah. So So part A, normally the problem A is at transfer stage, and normally part B, if you look at, it will be at service load stage. Okay, alright. So at transfer stage, you use the P initial to calculate. Okay, use the P initial to calculate, and then your moment is you use the this MS WL squared over 8 is the total, right? Okay, so you can have MS cell weight, which is equal to W cell weight plus L squared over 8, and then MS superimposed dead load due to superimposed dead load, which is W superimposed dead load multiplied by L squared over 8, and here MS superimposed live load due to W superimposed live load over L squared over 8. Okay, all right. Why do I split this one? Because at the transfer stage, the MS you use is MS cell. Okay, you use MS cell. Use MS cell weight only. Okay, and then at the service load thing, you use P effective and MS total. MS total, that means this one plus this one plus this one. Understand? Yeah? Alright. Now, here I haven't talked about the equation yet, right? I just tell you the P, you use P initial, and pre-stressing force you use P effective. Okay? Now the P initial and P effective is given to you, right? So you say that given PI is equal to 1325 kilonewton, right? Problem A. And then if you look at my B, I say assume 20% losses from PI. That means P effective is 0.80% of PI. Understand? Okay? So in the problem, test 2, I give you P initial, right? And then I tell you percentage of losses. Okay, so your P effective is calculated based on P initial and losses. Understand? Yeah. So this one you need to be okay. So let's say here I say calculation of P initial and P effective given losses. Okay, so I can give you PI and give you, let's say, 20% losses. That means the P effective will be equal to PI multiplied by 0.8. That means only 80% left, right? Initial, and then you have 20% losses. That means whatever left is just 80%. So the P effective is equal to 0.8. Okay, for this problem, right? So let's say if this is losses is 25%, then this will be 0.75 because 75% left. If this is 10%, it means 0.9, right? Because you still have 90% left. Okay. All right. So in this problem, I give you PI, right? And you calculate P effective. Now I can also give you P effective, 20% losses. Then you calculate PI, right? So PI will be what? Will be P effective divided by 0.8, right? So PI is P effective divided by 0.8, right? Okay, so you need to be careful, okay? if I give you PI losses, then P effective is PI 0.8, okay? Multiplied by 0.8. Yeah, I can give you P effective and 20% losses, then you have to back calculate. So remember, 20% losses, that means 80% left. That means 0.8 left. Okay? Alright? Understand? Huh? Okay. So this is easier. This one, maybe you can make mistake, but the thing is, you just have to be careful. Alright? Okay, huh? Okay, so here, section properties, calculation of moment, calculation of PI and effective, right? Okay, normally, let's say this is a sections. Normally, this is our strengths. These are our strengths. Okay, these are our strengths. Say this is a neutral axis. Neutral axis. Okay. Now, the strength is at a certain distance from the neutral axis, and that distance is called eccentricity, E. Okay? Alright. So, for example, in this case, my strength will be here. Let's say. Okay? So E will be measured from the neutral axis up to the centroid of the strength. Okay? So we got this one, right? So in this case, what is my E? In this case, what is my E? The neutral axis is in the middle to the centroid of the rebar or the strength. Here in this case, I give you the cover. Okay? I think in this problem, right? I give you this value, right? 150, right? Right? And this is 300, right? So the E would be 300, subtract the 150. Okay? Alright, huh? Okay. But in the final exam, okay, I give you both these values and these values. Understand? So you need to pick this one, not this one. Understand? Huh? Okay, huh? Let's say this. Let's say this is 180. Let's say this is 120. Okay, right? So the E is equal to this one, measured from the neutral axis to the strength, not from the bottom. Okay? Now the reason in this case I put 150 because even if you pick the wrong one, the number is still correct. Understand? But in the final exam, these are two different numbers. You need to pick the correct one. The eccentricity is always measured from a neutral axis. This is the location of the strands. This number is telling me the location of the strands from the neutral axis. This number is telling me the location of strands from the bottom. Okay? It's always E is the location of the strand from the neutral axis. Okay, huh? Alright. So now now we do the calculation of stresses. Okay, A, calculation of F1 and F2. Okay, F1 and F2. F1 and F2. Okay. A is at transfer stage. So A will be at transfer stage. Okay. And we need to calculate at midspan and at midspan and at support. mid-span and at support. Yeah. So that is why I do the middle to right. Okay. At mid-span, I have to calculate F1 and F2. At mid-span, I have to calculate F1, F2. At support, I also need to calculate F1, F2. Okay. So let me write here F1. So the formula is this: is axial. The stresses is due to pre-stressing force, right? Axial load. So axial load is negative P over A, right? The pre-stressing force, this strength is pulling and inducing the pre-stressing force here, like this, okay? So, and the pre-stressing force has a axial stress, right? Create a compressive axial stress. So, it's P over A. And in this case, we use PI over A. Okay? Alright. And then we have the pre-stressing moment, because the pre-stressing force is applied at an eccentricity. Okay? If this thing is applied at a centroid, then this is a uniform stress, compressive stress. But if it is applied offset, not only will have a compressive stress, but it also has a bending moment. Okay? We call the pre-stressing bending moment. Okay? And that pre-stressing bending moment is P multiplied by E. The pre-stressing force multiplied by the eccentricity. Okay? One more time, huh? Let's say I use this one, right? I use this one. If my pre-stressing force is acting in the middle, there's only pure compressive stress. If as soon as I start moving, then I induce a moment. Okay? Understand, huh? Okay. So that is why I have. Okay, let me do this. Here. Okay. Here at mid-span. Here, the first term is the stresses due to P. Okay, this is stresses due to P. Okay, this one is stresses. The second term is stresses due to PI, P times E, the pre-stressing moment. Okay, all right. And then the third term is stresses due to external moment. External moment. Okay? So at transfer stage, you always have, actually whether it at transfer stage or at service stage, our stresses is due to axial force, pre-stressing force. Okay, stresses due to, I just write properly. At span here, F1, F2. F1, F2. First is stresses due to pre-stressing force P. Okay, so this is negative P over A, also negative P over A. Whether it is top or bottom, is negative P over A, negative P over A. So the second term is stresses due to pre-stressing moment. pre-stressing moment is calculated as P times eccentricity. Okay, so this one, because it's a transfer stage, so I use the P initial. Okay, here, this is pre-stressing moment, P times E, okay, divided by S1. Okay, this is the pre-stressing moment, right, divided by S1. So here is pre-stressing moment divided by S2. This is P divided by A, P divided by A. This one is pre-stressing moment PE, P multiplied by E divided by S1. Here, pre-stressing moment P times E divided by S2. Because this is transfer stage, so I put a PI. Okay? So, this one here. Alright? Yeah. Then the third term is stresses due to external moment. Okay? External moment, this is MS. So here is MS divided by S1, MS divided by S2. Okay? Alright? Just three terms only. 1, 2, 3. Okay? First one is stresses due to pre-stressing force, P. Is POA. Second term is stresses due to pre-stressing moment. Pre-stressing moment is P times E. Okay? So P times E. Here you divide it by S1 divided by S2. Okay? Here is stresses due to external moment, MS. MS divided by S1, S2. At the transfer stage, we are using only the cell weight moment. Understand? That's why I say here, at the transfer stage, you use PI for P. You use MS cell weight for moment. Okay? Alright? That is why now you can see why I asked you to calculate S1, S2 first. Okay? Alright? First, because you need this value here. Okay? And then, why I asked you to calculate the loading as well as all this moment, right? Because I need it here. Understand? Alright? So what I suggest you to do, is to use the T2 and rework it. Okay? And rework it, you can discuss among yourself, cross-check each other. Okay? Alright? And then you pass it back to me. Because right now I couldn't give you the marks. Cannot. Definitely give out. Because there's not everywhere there are mistakes. I don't know how to give the marks. That means is if I want to give the marks, it's probably below 10. Okay, so I need you have to rework it, got it correct. Also as a practice, right? And then you guys can access my past year question here, right? Can you access the past year question?
Yeah.
Only you can. Then you just maybe take the past year question, use one or two problems to work on it. Okay? To work on it, just to get yourself, because unfortunately I will not give you this formula. Okay, so you have to memorize it. And it is also not open book. Alright, so that is why I write out these terms for you. Only 3 terms only. Okay, first the stresses due to pre-stressing force. Second, stresses due to pre-stressing moment. And stresses due to external moment. Okay, alright. So that is why explain this to you. Okay, stresses due to pre-stressing force is just the force divided by the area. Okay, all right. Stresses due to pre-stressing moment is the moment divided by S1 or S2. The S1 is what we call the section modulus. Section modulus. Okay. Modulus. This is section modulus at top, and this is section modulus at bottom. Okay, so this part you should get it right because I already give you this value, and this value. So it's just mathematics, right? Then come to calculation of moment. This one you need to be careful. Because this one you need to calculate yourself. That means the beam self-weight. Okay. This will be given to you. This will be given to you. Okay. All right. So then you just have to calculate the moment. The moment at the midspan, which is WL squared over 8, or simply support. Okay. Right. Then calculations of PI and P effective, right? Here I should also do calculation of pre-stressing moment. Okay, pre-stressing moment is either P initial multiplied by E or P effective multiplied by E. Okay? P initial, P effective is here. E is this one. Alright? So these 3 steps, 1, 2, 3 steps, you should get it right first. Okay? When all these values are right, then you do this one. Okay? But I think maybe as Adia or you do not have the so because you did not include the E, right? Correct. You do not include the E. Okay. So I think of 6 of you, I think she has the more complete one. It means she know how to write this equation, right? You can write the equation. You also can write the equation. You include the E, right? You see you include the E. But then you also include the E at the top. Yeah, right? Here PIOA, pre-stressing moment divided by S1 or S2, M divided by S. So I think at least has the equation. Okay? I think 4 of you don't even have the equation. So okay? Alright now? Okay, so that's why I want you to rework this practice. Okay? Alright? Okay, now here we do it at the midspan. We also have the one doing at the support. Okay, now at the support, unfortunately I have to erase this. Okay, maybe I'll bring it over. So here midspan, and here at support. In this case, the left support and the right support is the same. Left support, midspan, and right support. So we just do one. So at the support, we also have F1, F2. Okay? So we also have 3 terms, 1, 2, 3. Okay? The first term is the same, PI over A. PI over A. Okay? Alright? So if you have calculated this, you just no need to recalculate again, just put in here. Then the second term, pre-stressing moment. If you look at my strands, so my strands is not straight. That means my strand is like a parabola. So when I do a parabola, what is changing? This is changing, right? And the midspan is like this. And when you get closer and closer to the support, the strand is going up, right? That's why it is the strand is going up. Understand? Anyone has a ruler? No one has a. Or maybe, let's say this is a strand, right? This is a strand. I use the paper to write. This is my neutral axis. So we can see the eccentricity is reducing, right? From midspan to here, right? Understand, right? The eccentricity is the neutral axis to here. So this one is telling you that the eccentricity is reducing. And at the support, if you look at this problem, I say at the support it becomes at 300. That means at the neutral axis. That means at the neutral axis, that means this is, as it goes towards the support, it goes up to here. So when it goes up to here, that means the eccentricity is becomes 0. Understand? That means the second term is P times E, but this E becomes 0 at the support. Okay? In the final exam, the E also becomes 0. Okay? And then at the support, 0 moment. Right? Okay? So here, the third term, MS self weight at the support, this one becomes 0. Understand? Okay, so then this is very easy, just POA only. And you already calculated, so you just put over here. Understand? Okay, now the sign convention. Compressive stress, negative, negative. Due to pre-stressing force, whether top or bottom is compressive stress, negative, negative. Okay? And then pre-stressing moment, because the pre-stressing moment, the force is like that. The pre-stressing moment is like this, right? The pre-stressing moment like this, bottom compression, top tension. So bottom compression, top tension. Okay? And the bending moment, this bending moment due to the load like this, meaning like this. So the top is compression, bottom is tension. Top is compression, bottom tension. Understand? Okay? Alright. Here, first term is negative, negative. This one is top positive, bottom negative. And the third one is completely switched. Understand? Okay, or if you don't want to memorize, you just say compression moment. The pre-stressing moment is like this because the force is this way. Like this, compression, top tension, bottom compression. Okay? Okay, the pre-stressing moment, pre-stressing moment is like this. Bottom compression, top tension. This moment is like this. Bottom tension, top compression. Okay? Alright, so the only, okay? Now, you need to pay attention because I'm afraid that if you don't pay enough attention, this you mix up the sign. And when you mix up the sign, then of course the calculation will be incorrect. Just because you mix up the sign, the calculation is incorrect, it means very, very pity, right? Correct? Understand? Understand, huh? Okay. Now, here we say at transfer stage, right? We have done at transfer stage, midspan and support. Here, the B will be at service load stage, midspan and support. Understand? Okay? So I'm running out of room to okay. Let me just say, okay. At service load stage, you guys go back and do it, but I tell you what to change. You see, at service load stage, I say use P effective. That means you change PI to P effective. PI to P effective. Understand? A doesn't change. S1, S2 doesn't change. Whether it's service load at the transfer stage, the properties, section properties doesn't change. Okay? Only the effective force changes. The force changes from P initial to P effective. Okay? And then, at service load, MS cell weight to MS total. Okay? That's all only. So in other words, if let's say if you memorize this, right? So at the transfer stage, then the service stage, you just remember that my PI is exactly the same, except that my pre-stressing force changing from PI to P effective. And then my external moment is changing from just self-weight to total. Total, that means include the self-weight also. You don't say I just only this one. Because I use this one now, the service load stage, I use this tool. That is not right. You use the total. Okay? Right, can remember or not? Okay? So I think you go back there. Over the weekend, you work on it. Okay? And then this A, B, you rework it and pass it back to me. If you can do C, I think some of you do C also, right? Then also pass it back to me. Okay? I think the D and the E, I will not talk about it because otherwise you'll be overburdened. You just have to memorize too much. Because now for me is to get you past. So that's why this is the basic. So I want you to know the basic. You do it. I think if you finish the basic, because each one is 25 marks. Each question, 4 questions, each question 25 marks. If you finish part A, part B, right? Most likely you get 16 or 17 out of 25. You probably get 2/3 already. Understand? Then the 1/3 you just let go. And then you go and do the question 2. Understand? Okay. Now, today I only talk to you maybe question 1 and question 2. Okay? And then we find another day to talk about question 4. Question 3 is the shear wall. Okay? Shear wall, I think most people, if you can handle it, good. If you don't handle it, because the torsion design is easier. So, but I think you guys miss on the torsion design. So I think I will pick another day to talk about the torsion design. Okay? Very much like this format now. Okay? Means so that let's say each problem, let's say question 2, let's say question 4, you get 2/3 of the point. Let's say 2/3 of the point. Maybe you are talking, let's say, so you are talking about at least 45 or 50 points. Correct? What I'm saying. Okay. All right. Then the third problem. You just, because my concern is I don't want to overburden too much on it. So I just pick the easy one that you can remember, because shear wall can be quite complicated. Okay, If you have the time, then we talk about the shear. All right. Okay. So now the second problem is the earth retaining wall. That is relatively simple. Okay. All right. So okay, let me rest for a while. 5 minutes. Can someone help me to rub this one out? And then you. Huh? Oh, you want to take a picture? I think the acorn is not working, isn't it? Very a bit hot, isn't it? Okay, now the second question is, so question 2 earth retaining wall design. Now, so let's say this is the earth retaining wall. Okay. Now the earth retaining wall, the data that I give you is, I'll give you the height. Okay. I give you the wall thickness. Okay, let's say the height, let's say is 3 meters. Let's say. Okay. The wall thickness, let's say, wall thickness is let's say the wall thickness, let's say is 200. Okay, say the wall thickness is 200. So this one I'll give you, and then I'll give you the soil property. Okay, I'll give you the selving of the soil, right? Let's say 18 kilonewton per meter. Okay, and I give you the Ka, which is the active earth pressure. Let's say 0.33. Okay, and I also give you the surcharge. Let's say surcharge is 10 kilonewton per meter square. Okay, this is the surcharge. These are the things that I give you. Okay. Now, before I go on, in the pre-stressing, pre-stress concrete problem, the moment that we are dealing with is a service load moment. That means the load factor is 1.0. Don't use 1.4, 1.6. Understand? In the pre-stress concrete problem, okay, the moment is based on service load moment, not factored load moment. Service load moment, that means the load factor is 1.0. Don't use 1.4 times that load and 1.6 times live load. Okay, this is something that you need to remember. Okay, because over here, then we will talk about the factor load moment. Right? Huh? Okay. All right. Okay, so these are the data that I will give you, right? The height of the wall, the thickness of the wall, the soil properties, and then the surcharge. Mainly is this one and this one is the soil property. So soil property, I'll give you the sulfate of the soil and active pressure for the soil. Okay. This is the wall property. And this one also is the wall property. Okay. That means wall property. So the wall property is the height of the wall as well as the thickness of the wall. Okay, all right. Okay, and then the surcharge. Then you are to design the vertical reinforcement. Okay, you have to design the vertical reinforcement. Vertical reinforcement. Okay, vertical reinforcement in terms of, let's say, T12 and 200, T60 and 150, or T60 and 300, etc. Okay, all right. Okay, so this vertical reinforcement is because why are we have to design for this vertical reinforcement? Because this one, it has a cantilever moment at the base because you push it, right? Let's say this is the wall, the soil is pushing it. That's why you have a bending moment at the base. Okay, so the starting point is the calculation of bending moment. Okay, so but what is causing the bending moment must be the lateral load. So you start with the lateral load. Okay, so let's see. Yeah, lateral load on wall. This is the problem introduction. Okay, give you the overall picture first. Here, lateral load on wall. Okay, lateral load on wall is, let's say this is a wall. This is a soil, and this is the surcharge pressure. So you would have a triangular loading, okay, due to the soil. And then you also have a lateral pressure due to the surcharge. Okay, so the lateral pressure due to the surcharge is Ka times the surcharge. Okay, S is equal to the surcharge. Okay, so Ka times the surcharge is the lateral pressure. And here, maximum pressure, this pressure is 0 to maximum, right? 0 to maximum, and this maximum is unit, the soil weight multiplied by the total height multiplied by Ka. So that's why I give you this one and this one. Okay? All right? Okay, now we know that these are the two loadings, right? These two loadings. Okay, so we have bending moment due to the soil pressure and bending moment due to the surcharge. This is here. This is the lateral soil pressure. This one, sorry, this lateral due to surcharge. This one lateral load due to surcharge. This is a let me write this uniform lateral load due to surcharge. This one is triangular lateral load due to soil pressure. Okay, due to soil pressure. So, no, right? So here, then you go to do a lateral load on wall and cantilever moment, then the calculation of the cantilever moment at the base. Okay. So we have a bending moment here, right? Okay. Here is calculation of bending moment of lateral bending moment at the base. Okay, all right. So because we have two types of loading, that means we will have two types of bending moment, right? First is MS here. Here I start with the MS, unfactored load first. MS due to surcharge. MS due to surcharge is what? Pressure multiplied by the height give me the force, right? So this is Ka times surcharge, right? So this is the pressure. So the force is just this pressure multiplied by the height. That's my force. Ka times S multiplied by H. Okay? Right? And the MS due to the surcharge, because the force is Ka times S times H. Okay? This is the force, right? Okay? Acting in the middle, right? Okay? So this is equal to 1/2 of Ka times S H squared. So we can memorize this one. 1/2 of Ka S H squared. Okay? Okay. Now, MS due to the soil is equal to, this is Ka sigma S gamma SH, right? Okay. So the pressure, so the average pressure is what? Because it go from 0 to here, right? 0 to maximum. So the average will be half of this, right? Correct? Average pressure will be half of Ka gamma S H. This is my average pressure. Average uniform pressure, right? So the pressure multiplied by the H will give me the force, right? Okay, and this force here is acting from here is 1/3 of H, right? So here multiplied by 1/3 of H, okay, and that will give me 2 times 3 is 6. So 1/6 of Ka gamma S H cubed. 1/6 of Ka gamma S HQ. So you could remember this. Understand? So immediately you can say, okay, the moment due to my surcharge is 1/2 of Ka SH squared. This is 1/6 of Ka gamma HQ. Okay? Alright? So that means if you can memorize this formula, then you just stick it in only. So you can use this one, so you just use this number to practice. Understand? Okay? Now, this is a service load moment, right? In the design, we need to do the ultimate load moment, right? So ultimate load moment, M ultimate load factor. That means this service load moment multiplied by the factor, load factor. So the surcharge is 1.6. Okay, and then the lateral soil pressure is 1.4. Okay, the lateral soil pressure moment, service load moment multiplied by 1.4, load factor, this one MS surcharge with 1.6. In the problem, I already told you in the problem. In the problem, you will find that use the 1.4 factor for soil and 1.6 factor for surcharge. Okay? Because the surcharge is a little bit unpredictable. Because you really don't know what is going to be here. Is it a car? Is it a truck? Is it a lorry? Or whatever. Right? So that's why our load factor is high for the surcharge. Okay? Now, once you calculate the M ultimate, then you design for the vertical reinforcement. Okay? Right? And your starting point is first calculate the K, which is equal to M ultimate divided by BD square F sub CU. Right? Okay, first you calculate this one. MU is here. Okay? D normally I'll give you. Okay? D normally. B is what? Because this is our wall, right? Our wall is designed based on per meter width basis. So 1 meter basis or 1000 millimeter. That means this could be 30 meter, right? So we design per meter width basis, okay, and then we repeat. So that means because it is per meter width basis, the B is 1000 millimeter. Okay, this one normally is kilonewton meter, and then you need to convert it to 10 to the 6 Newton millimeter. Understand? Yeah. For example, this B here, this is my reinforcement at the back face, right? So let's say the thickness is 200, the D might be 150, but nonetheless I'll give it to you. Understand? Okay? So this is the D. Okay? This is the thickness of the concrete. D is only measured up to the rebar. Understand? Okay? D is called the effective thickness. Effective thickness. Okay? Because let's say the wall is like this, right? The wall is like this. Because this is a tangent zone, so the concrete is cracked here. So this part of the concrete is not effective. So the only effective concrete is this one. Understand? And that is a D. The D is called the effective thickness. TW is the total thickness. So effective thickness is the total thickness minus the concrete cover, because that concrete cover is not effective. Understand? Alright, let's say the concrete cover is 40 plus the bar diameter, that's why, but normally D will be given to you. Okay? But when you go out to work, that's how you calculate the D. Understand? Always remember D is the effective depth or effective thickness. Okay? Then, after you do the K, then you do the Z over D, right? D over, I think is Z over H. Is it Z over thickness? Z. I think, I do not know your convention is what. I think is, the code is K is Z over, Z is the lever arm. Okay? I think it's Z over D, that's correct. Lever arm. Okay? Z over D, this one is 0.50 plus square root of 0.25 F multiplied by K divided by 0.9. This is given in a code, right? If the code will be given to you in the final exam. Anyone bring the code? You should. Okay, right here, okay? The design formula for rectangular beams is section 3443. So you must know how to verify the one. Okay? So you can see that K is equal to M dD square, M divided by dD square as C. Right? Then after that, you do the Z divided by D. Here they put the D on the other side. Say is Z equal to D multiplied by the bracket here. So normally I'll do a Z divided by D equal to this bracket, 0.5 plus square root of 0.5 minus K divided by 0. Okay? Alright? Okay, then after that you do the A, S is equal to M divided by 0.9 Fy Z. Okay? Alright. Z, this one here is the lever arm. Lever arm is actually the distance between the compression force and the tensile force. Okay? Because let's say this is a concrete. This is the rebar. Here is the tension, right? Okay? And the concrete, the rebar is concentrated. The rebar is in area. So the rebar, the concrete actually has a distributed pressure, distributed stress on the concrete. Okay? So this is the tension. And here, this is T, right? And then, because this is a distributed stress, so this is the compression resultant. Okay? Compression resultant. Understand? No? Because whenever you have a distributed load, you have a resultant. Okay? If it is a triangle, just like this one, yeah? This is a uniform stress, so the resultant in the middle, right? This is a triangular stress, the resultant is 1/3. So here also, this is a parabolic stress, so there is also a resultant, right? And this one is Z, the lever arm. You have a tensile force, compression force, the lever arm create the moment, right? That means the tensile force and compression force create the turning moment. Right? Like this, like this. I have tensile force, compression force, right? Create the moment. Understand? Vanya, are you getting tired? Okay. All right. That is why. So you can see that the moment is actually equal to T times the moment arm, right? Okay, so that means my T is equal to M divided by Z. My moment divided by moment arm is my tensile force. So you can see this one is actually equal to the tensile force, right? The tensile force divided by the tensile stress give you the area. Right? Okay? Understand? No? And this one is Z is the, okay, where is D? D is here. Okay? Z is this one. Okay? D is this one. Which one is bigger? D is bigger, right? So Z is actually only a partial of D. So normally when you calculate 0 Z over D, you can come up with, let's say, 0.89, 0.85. See what I'm saying? That's why you can see 0.50 plus something. And this one, this also 0.25 minus. I forgot the minus. Huh? So you can see that this thing is a fractional number. These things, when you calculate out, okay, is a fractional number. Could be 0.85, 0.8. So what does that mean? That means, let's say this one is equal to, let's say, 0.85. That means my Z is 85% of my D. Understand? Okay? All right. So once you have, then you can calculate the area needed. Then you have to convert that to the rebar size and the rebar spacing. Okay? So I think I will stop here. You work on that one based on the data. Okay? And then Friday is a little bit tight because I think I will have to start. Maybe Monday you have to, maybe if you are not sure, you can show me your results and keep comments on this. Okay? So these are the two. Okay? These are the two. And then the torsion. Okay? When is your first final exam? Huh? Monday. Monday is your first final exam. Huh? Monday. So I think you better start because your Tuesday is this one, right? Monday, what morning? Huh? 3 o'clock. Then maybe I think tomorrow you don't have any final exam, right? Tomorrow I have a final in the morning, 9 to 11. Then because I think Friday evening I will talk to you about the torsion design, so that I think over the weekend you can practice. But this one today you can start practicing already. Understand? While the thing is still fresh. Okay? Alright. Tomorrow I was thinking of maybe 3 o'clock. 3 o'clock to 4 o'clock. Okay. Alright, so I think we'll stop here.
For the reward, is it on Monday?
Huh?
Is it the reward of...
Yeah, this one you tidy it up, then you pass it to me maybe after your your final exam also can, then you can do the grading. But I think you should finish before then if you have some time to practice. Just, I think 6 of you just discuss among yourselves. Okay.
Same to you.
I think I would say individually you do it first, then you get stuck. When you get stuck, then you check up on each other. What's your problem? What's your question?
No, listening to you, we aim for your right to, or we uploading on.
Okay, because on Tuesday your final exam is on 9. No, if you want to check the results, then you check it at 3 o'clock. See what I'm saying? So that means tonight you have to work on it. And my advice is you should do it individually first, then you get stuck, then you discuss. Alright? Okay, yeah? Alright, so I need someone to help me rub this one off. Thank you very much.
You want to